This is Tim O'Brien coming to you from Seattle in November of 2025. And this is part 3 of a series on databases and the emergence of vector databases. Now, if you're just joining us now, I'd strongly recommend that you start with part 1. I'll talk about a 20-year history in which we moved from relational databases to many different kinds of databases to support scale. And I'd also recommend part 2, in which I talk about vector databases and some of the fundamental technologies that lie at the heart of modeling information. But if you're already familiar with vector databases and the database landscape and how it's changed over the last 2 decades, you can start to jump right into vector database options in this episode. So a quick recap. In part 2, we explored the fundamentals of vector databases, those strange new systems that store mathematical fingerprints of meaning. Instead of traditional rows or JSON documents, we learned what embeddings are, how models like OpenAI's text embedding ADA002 convert text into 1,536 dimensional vectors that capture semantic meaning. We also talked about why traditional databases struggle. Why do we need vector databases? And that's because indexes and B trees were not designed for, quote, find the 10 most semantically similar documents. You need the specialized algorithms like ANN, HN-W, or IVF. We also mentioned the AI gold rush. There's so much money flowing into this space. Generative AI spending is projected to hit $644 billion just this year, and every RAG application needs somewhere to store its vectors. We also talked about a fundamental shift. We're moving from exact matches to similarity searches, from discrete fields to data that's in a continuous mathematical space. Now in part 3, we shift from theory to practice, and we're going to survey the actual vector database landscape, what I'm calling the contenders. And fair warning, this episode is going to be fairly technical. I will explain some of the key concepts, but the latter half of this episode will dive unapologetically into implementation choices, cloud cost, performance characteristics. The goal is to arm developers and data architects with a snapshot of the state of the vector database market as of late 2025. This space moves fast. What's true about performance or pricing today might be outdated next quarter. Still, the fundamental patterns and trade-offs outlined here should help you navigate whatever the landscape looks like when you're making your own decisions. Before we dive into the actual databases, let's talk about how these databases store data. A common point of confusion for teams new to this area is exactly what a vector database stores. Are we indexing documents? Are we creating tables? In practice, you usually start with data you already understand, say a text document, a product catalog entry, a user profile. You run that through an embedding model to get a vector, a 1,536 dimension floating point array for text. Then you write a record that typically consists of an ID, the vector itself, and some metadata, perhaps something like an original title or a URL, some tags, a category. Under the hood, most vector databases organize these records into collections or indexes, not into relational tables with foreign keys and joins. Conceptually, it resembles a simple table. One column might be the vector, but the engine is optimized around that vector field, rather than around multiple columns, transactions, or joins. Some systems will happily store your full document content alongside the vector, but others encourage keeping the source of truth elsewhere, like Postgres or S3, and storing only enough metadata to retrieve or identify the item later. Importing data into a vector database does 2 things at once. It persists the vector and the metadata records, and it builds a similarity index over those vectors. That's where the algorithms come in. As you insert vectors, the database plugs them into a data structure, often an HN-SW graph or an IVF index or something similar. And these indexes are sometimes updated immediately, but sometimes there's buffering, and indexes are built in batches. The payoff is that later you can efficiently find nearby vectors without scanning through all 10 million or 10 billion individually. How vector databases are queried. Querying a vector database feels less like select star from orders and more like querying a search engine. The typical flow is this. 1. Take your query input, text, image, audio, and produce an embedding vector using the same model you used at write time. 2. Ask the database, give me the top K nearest neighbors to this vector, optionally filtering by some metadata condition. In code, this is usually a client library call or an HTTP, a gRPC request. This is not an ad hoc SQL query. For example, if you're using Python, you might make a function call to .query with a vector parameter and a filter parameter. For example, you might send it a vector and say filter where the region is US, and then say I want the top K results, the top 10 results in terms of similarity. And this will return the top 10 results that are in that region US. Most of the specialized vector engines provide their own APIs or query languages. Pinecone, Milvus, Weaviate, Qdrant, they all expose REST or gRPC endpoints and offer client SDKs for languages like Python and JavaScript. A few support SQL-like syntax or GraphQL wrappers. Weaviate, for instance, has a GraphQL API, but under the hood, it boils down to the same thing, a nearest neighbor similarity search on a vector, plus optional structured filters on the metadata. The ability to combine similarity with metadata filters is critical for so-called hybrid search. For example, you can find items similar to this vector where the product type equals database and the region equals US. As for standards, we don't yet have a JDBC for vectors. The closest thing to a common interface that has emerged is at the framework level. Tools like LangChain, Llama Index, and various retrieval-augmented generation libraries define a generic vector store interface, and they provide adapters for different backends. For example, LangChain can plug in Pinecone, Weaviate, Qdrant, Chroma, and all of those are behind a common API. In the relational world, databases that added vector extensions, Postgres with pgvector, MySQL HeatWave, Oracle 23c, those can all be accessed over traditional ODBC and JDBC drivers, but the dedicated vector databases mostly expose their own wire protocols. This space is still very new. At the moment, portability comes from these abstraction layers rather than a universal query standard. So let's get to the heart of this episode, the contenders. These are the vector database options in late 2025. Broadly, the ecosystem can be divided into open source engines, which you can self-host, often with optional managed cloud services from the project creators, and fully managed commercial services. I've selected 3 options for these categories. First, open source engines. Milvus, M-I-L-V-U-S. Milvus is a distributed vector database built for billion-scale workloads. It supports multiple index types, HNSW, IVF, and disk ANN, and an optional GPU acceleration. Milvus is licensed under the Apache 2.0 license, one of the most widely adopted vector databases with strong community support. The next is Weaviate. Weaviate is known for hybrid search capabilities. This combines vector similarity with keyword search and filters. It features GraphQL querying and a modular architecture. It's BSD3 licensed, and it's a popular choice for RAG applications and LangChain integrations. Next is Qdrant. Qdrant is a Rust-based vector search engine praised for performance and rich metadata filtering. It's designed for multi-tenancy with separate collections per use case. It's licensed under the Apache 2.0 license, and it has a strong balance of speed and query expressiveness. Next are the commercial managed services. First is Pinecone. This is the original managed vector database service. It's fully serverless and has simple APIs. It handles all scaling and indexing automatically. It's the most widely used according to surveys, but it is higher priced and has some vendor lock-in, as it is completely proprietary. The next is Zilliz Cloud. Zilliz Cloud is the managed version of Milvus. It combines open source flexibility with enterprise support. It's rated highly for performance and ease of use. It's a great option if you want open source under the hood, but you don't want to take care of operations. You want that managed for you. And last are Weaviate Cloud and Qdrant Cloud. So these are both managed offerings from their respective open source projects, feature parity with self-hosted versions, but with operational burden removed. The pricing typically starts from around $25 to $300 a month, depending on your configuration. So the differences between these contenders do matter. Pinecone prioritizes simplicity and scale, but is a closed service. You trade some flexibility for convenience and will incur higher costs at large scale. Milvus gives you an open source core with the option of a polished enterprise managed cloud through Zilliz. Weaviate and Qdrant focus on open flexibility, hybrid search, customizability, on-prem or cloud as needed. So these are the top contenders in the vector database category. And these are the databases that are specifically designed for similarity search, for vectors. Depending on the size of the problem you're trying to solve, you may not need a specialized vector database. Traditional databases, relational, document, search, and even caching systems are rapidly adding vector search capabilities. Depending on that scale and the requirements, these features might work well enough, especially if you'd prefer not to introduce a whole new system into your architecture. So here's a quick tour of how some of these traditional or established databases have started to add vector support. Let's start with Postgres. pgvector, the popular open source database, added vector search via an extension. It's great for teams already using Postgres who want to keep everything in one place. It works well for moderate scale, a few million vectors, but it starts to hit limits with billions of vectors since it's not distributed. Next is MongoDB Atlas. MongoDB Atlas added vector search to their cloud offering. This lets you combine traditional document queries with vector similarity. This is only available in their paid cloud service, not the open source version of MongoDB. Elasticsearch and OpenSearch. The search giants naturally added vector capabilities, excellent for hybrid search, text plus vectors, but complex to operate and a bit resource intensive. Then there's Redis. Redis is an in-memory cache. They've added vector search for blazing fast queries. This is perfect for small datasets that need sub-millisecond response times. MySQL HeatWave. This is Oracle's cloud-only MySQL service with vector support. Niche product mainly for existing Oracle and MySQL shops. Oracle Database 23c. This is Oracle's flagship database, but it now does vectors too. Enterprise focused with enterprise pricing. Their pitch, why add another database when Oracle can do it all? Azure Cosmos DB. So this is Microsoft's globally distributed database. They've added vector search. Good if you're already using the Azure ecosystem and need a worldwide distribution. Then there's Snowflake. It's a data warehouse. They added vector functions for analytics, not for real-time queries, but useful for batch analysis, combining vectors with business data. Then you got Databricks, similar to Snowflake, focused on data science workflows and batch processing, good for experimentation, not necessarily for serving a production website. And they've got cloud providers, AWS, Google Cloud, Azure. They're all adding vector capabilities to their database services. I just got an email today about Google Spanner, adding support for vector similarity searches. Everyone wants to check the We Do Vectors box. For many teams, using that familiar database with vectors is good enough. It avoids introducing another moving part. And if your scale is modest, if you only have a few million embeddings, if you don't need sub-10 millisecond latency on complex queries, adding pgvector to Postgres or using Elasticsearch vector search or Mongo's Atlas might be the most pragmatic route. On the other hand, if you find yourself pushing the limits, tens of millions of embeddings, very high concurrency, needing millisecond latencies, that's when the dedicated vector databases we discussed earlier start to win. There's another interesting thing to talk about, it's graph databases. Graph databases like Neo4j deserve some special attention in the vector landscape. They combine explicit relationships, who knows whom, with implicit similarity, what's semantically similar. And it creates some powerful query opportunities. Two compelling examples from the graph plus vector use case: friend product recommendations. Find products similar to what I'm looking for that my friends have purchased. This combines vector similarity with graph traversal. Neither technology alone could answer this efficiently, but when they're combined, you can do this. The other is fraud detection. Combine transaction pattern similarity vectors with account relationship networks, graphs, to ask, find suspicious transactions that are connected through previously flagged accounts. So other graph databases like AWS Neptune, TigerGraph, and ArangoDB are adding similar capabilities. While powerful, this graph plus vector system adds a significant complexity, and they're best suited for very advanced use cases, where you truly need both relationship traversal and similarity search at the same time. Now let's talk about this operational paradigm shift. Why vectors demand a new kind of database? And let's zoom out and talk about why dedicated vector databases exist, despite every incumbent database trying to add vector features. History has shown that whenever a fundamentally new data workload emerges, it often warrants a new database paradigm. Relational databases like Oracle were kings of transactional workloads. The rise of web-scale, unstructured data, and distributed systems gave us NoSQL databases like Cassandra and MongoDB. And this wasn't because someone felt like reinventing a wheel, it was because the requirements, the scale-out, the eventual consistency, the flexibility of the schema were beyond what old systems were built for. Similarly, stream processing needed specialized systems. Time series data benefits from specialized engines. And there's more and more examples. Vector data is different enough that it benefits from a purpose-built approach. It's got size and search patterns that are different. Vector embeddings are huge. A single text paragraph becomes 6 kilobytes of data. Finding similar vectors requires specialized math that traditional databases were not designed for. They're built for scale. Purpose-built vector databases handle billions of vectors by distributing data across many machines, using specialized hardware like GPUs. Traditional databases struggle at this scale. Vector databases optimize for bulk loading and fast similarity search, not transaction guarantees. They're more like search engines than traditional databases. So a purpose-built vector database is different from your traditional database, and the industry is voting with its dollars. The vector database market blew up from an estimated $1.5 billion in 2023 to a projected $4.3 billion by 2028, nearly tripling in 5 years. Another analysis projects it to reach $7.3 billion by 2030. And these kinds of growth numbers are rare in the database world. Databases are mature and usually fairly slow growing. Even the new ones take time to hit. And this signals a gold rush of sorts. And indeed, investors have poured money into this space. Pinecone alone raised $100 million in early 2023 on a $750 million valuation. And other startups in this area, Weaviate, Zilliz, Chroma, they have raised tens of millions. You don't see that for a feature. It's because there's a belief that this new category is being established, and it's one of the foundational technologies for generative AI. There's another angle. Look at the hardware that's being thrown at generative AI problems. Microsoft reportedly built an AI supercomputer for OpenAI with 10,000 GPUs. And just recently, they announced a new cluster with over 4,600 of NVIDIA's latest GB300 Blackwell GPUs. And that's not cheap. Every day, we're seeing another announcement that tens of billions of dollars are being invested in data centers, and these data centers are being built for GPUs. In fact, 80% of that $644 billion projected spend for this year is hardware. So this is cutting-edge infrastructure designed to handle tasks like massive embedding generation and vector search across web-scale content. And we are deploying thousands of GPUs, hundreds of thousands, with high bandwidth interconnects just to handle vector operations. It's clear that this isn't just a traditional database. The winner in vector databases will be the ones who can leverage such hardware and architectures to make AI applications efficient and scalable. My prediction, despite every general-purpose database vendor bolting on a new vector feature, we're going to see one or two vector-native platforms rise to become the de facto backbone of AI applications. It's not that the others can't do vector search, it's that the dedicated systems will do it so much better at scale and with lower total cost due to architectural optimizations. So if you're building something that has to scale or has the potential to scale, you should likely opt for a purpose-built vector database. That being said, many applications we find with good enough vector capabilities in a traditional database until they hit a certain size. And this approach is often to start simple, reuse what you have, and only graduate to a specialized vector database when needed. But it's telling that companies like Pinecone have already attracted hundreds of customers and 15 plus POCs at Fortune 500s, or that tech giants are building their own internal vector search services. It means that this technology is here to stay. So to round out the survey, let's talk about scalability in practical terms. If you find yourself with a data set of, say, 100 million embeddings, how do the various options cope? What does it take to search billions of vectors with low latency? First, let's talk about cluster and sharding. Most production-grade vector databases are cluster-based for large deployments. They partition data across multiple nodes and sometimes have special roles for those nodes. For example, a coordinator node versus a data node. Let's use our key players as examples. Milvus. Milvus scales to 10 billion plus vectors, by spreading work across specialized nodes. Complex to operate, but proven at scale. Weaviate. Weaviate uses sharding to distribute data across nodes. The trade-off is there's more nodes and higher latency. Qdrant, it's been designed for many small collections rather than one giant index. It's great for multi-tenant applications. And Pinecone is the service of choice for many. It's a fully managed service that handles all the scaling details. You pay and they scale. In terms of real-world scale, for teams using vector databases, you've got Spotify. They have billions of song vectors for music recommendations. Pinterest has billions of image embeddings for visual search. Instacart has billions of product embeddings, and they're pushing the limits of Postgres. And GitHub Copilot has billions of code snippets for AI-powered code completion. Now, there's going to be many blogs out there about what tools they're using, but at this point, the stories seem to change from month to month. I'll tell you something. Some of these companies are probably building their own customizations on top of the open source options that we've discussed in this episode. But the real secret is that most companies really don't need to operate at those extremes. If you need to do similarity search with vectors, you probably don't have the scale of Instagram or the scale of Facebook. If you have 5 million vectors, you can probably run that on one beefy machine with pgvector or a single node Milvus or Weaviate instance. You don't really need a fancy distributed setup, but everyone does like to imagine that they might grow to Google scale. So these products are designed to scale out if needed. Another crucial trade-off for vector databases is memory versus disk. And this is whether to keep the vectors and indexes in RAM or allow them to spill to disk. There are some products like Redis that allow for in-memory indexing and storage of vectors, and it's very fast. That you can achieve sub-millisecond response times. In-memory search is faster, but it limits the dataset size to your RAM capacity, and RAM can be expensive. On-disk indexes with smart caching can handle much larger datasets with slower, but sometimes acceptable query times. In-memory indexes are fast, 1 to 2 millisecond queries, but expensive. Storing a billion vectors might need 6 to 12 terabytes of RAM. Disk-based approaches trade speed for cost. Queries take 10 to 100 milliseconds instead. But you can use cheap SSDs instead of expensive RAM. You choose what you need based on your latency requirements and budget. But often what drives memory or disk is what approximate nearest neighbor you're using. Are you using HNSW? Are you using IVF? Or are you using the Microsoft Research developed disk approximate nearest neighbor? And that disk-based approximate nearest neighbor leverages on-disk indexes with smart caching. And that's often what most large installations use to keep costs under control. But cost is a whole different area. And let's talk about what to budget for a vector database. Deploying a new database isn't just a technical decision, it's often a financial one. How much do these vector databases cost, and what are the components of that cost? So let's talk about the fully managed services first. And these are the managed service providers, Pinecone. Pinecone will charge you a base fee of about $70 a month per million vectors. But then there's also going to be a charge for volumes of queries. About 100 million vectors will cost you $7,000 a month. Add more to that and you're looking at approximately $200 to $300 a month for a starting price. And then scale up to 100 million, you're looking at a couple thousand a month. But it's all depending on what your traffic is, how much you use it. Sky is the limit for Pinecone. Zilla's Cloud is a little more approachable. As a starting point, you can pay about $100 a month. You're going to pay $20 to $65 per month for a million vectors, depending on your performance tier. And 10 million vectors will run you about $200 to $500 a month. It's going to be the same as Pinecone, though. You're going to be charged for the volume of queries that you push to this managed service. Weaviate Cloud, $25 a month for a million vectors, and about $295 a month for a small dedicated cluster. So when it comes to managed services, you're looking at a starting price point of about a couple $100 a month for production, and that's for 10 million vectors. If you go up to 100 million vectors or a billion, then your price is going to go up quick by orders of magnitude. So again, 10 million vectors, probably a couple $100 a month. 100 million vectors, then you get into the thousands. More than that, it's going to be expensive. What about self-hosted costs? There could be some cost advantages, but it's usually going to work itself out to about the same costs as managed services because there's overhead. You're going to have to pay operations professionals to patch and update VMs. You're going to have to watch hardware. You're looking at, again, about a couple $100 a month for 10 million vectors on a single server. and about $4,500 a month or more for 100 million vectors and up on a cluster. And here's the catch. You're basically becoming your own database vendor. You're going to have to add in some cost for that. You'll need someone who understands distributed systems, can debug index corruption at 3 a.m., and someone who knows how to tune performance. Think of it as needing a vector database DBA. The engineering time often costs more than the servers themselves. But the real cost of a system like this is often not the vector database or the infrastructure it's running on. The embedding generation itself can be a significant cost, but it depends on the volume of embeddings you have to create. OpenAI's ADA002 is $10 for 1 million documents at 100 tokens each. If you have a large corpus embedding Wikipedia, that's billions of documents, thousands of dollars. If the model changes, if you have to switch from ADA002 to a newer model, you have to re-embed everything. If there's new documents added daily, you're going to have continuous embedding costs. And that's also just the first step. You also need a pipeline to chunk documents intelligently. Bad chunking equals bad retrieval, error handling for failed embeddings, API limits and network issues, and version tracking. Many teams underestimate this data prep phase, and it's not just the $10 per million, it's the engineering time to build a reliable embedding pipeline. So here's a quick budget guide just to round out the cost section. For development, less than 1 million vectors, free to $100 a month. You could probably run it on your laptop. For medium scale, 1 to 10 million vectors, you're talking about $300 to $500 a month as a starting point. You could pay more for redundancy. A large scale, 100 million vectors and up, starts at about $3,000 to $7,000 a month. And with enterprise requirements like redundancy and high availability, double that amount. For extra large 1 billion plus vectors, this is where your cost is really going to start to depend on what is your performance requirement. If you need ultra fast responses for billions of vectors, the sky is the limit. I mean, you might be spending $250,000 or $500,000 baseline for this cluster. But if you can make some compromises on speed, you might be able to achieve a lower price, like maybe $20,000 a month or $50,000 a month. It's still going to be expensive. This is going to be an expensive investment, but it's not even the real cost in the generative AI space. And this is what catches teams by surprise. That $7,000 a month vector database bill, it might be the cheapest thing in your AI application. Consider a typical RAG application. Assume you're using GPT 5.1. That's, I think, $15 for 1 million output tokens. And a busy app can easily burn $20,000 a month on chat completions alone. Re-ranking. If you're using an LLM to re-rank your top 100 search results, that's 100x more API calls. Real-time embeddings. Need to embed user queries on the fly? GPU instances run $1 to $3 an hour, 24/7. Data labeling. Improving retrieval quality often requires human-labeled relevance data, and that's expensive. Teams often obsess over whether to pay Pinecone $500 or self-host for $300 while burning through $15,000 a month on LLM calls. Always profile your complete AI stack costs, and the vector database is important, but it's rarely the most expensive thing on your bill. In closing, vector databases bring a lot of power, but they're not magic. You still have to design your system thoughtfully. The good news is that whether you prefer open source and full control or managed and hands-off, there's an option out there for you. And the landscape is evolving so quickly that what's true today in late 2025 will almost certainly be surpassed by even better technology in the coming years. So now that we've explored the landscape from 426 different database systems to the newest vector database Contenders, you might be feeling a bit overwhelmed. How do you navigate this complexity? How do you avoid the pitfalls that come with so many choices? In part 4, we're going to step back from specific technologies and establish what I call the North Star principles, timeless guidelines that apply regardless of which database you choose. These aren't tied to Postgres or Pinecone or any other specific vendor. They're hard-won lessons from 25 years of breaking databases and occasionally fixing them. What we're going to cover is how to choose wisely when you have 426 options. Spoiler, it's not about picking the newest or the coolest. It's about picking the right database for the right use case. We're also going to talk about why going deep matters. Over the last 20, 25 years, we've lost DBAs, and what we've also lost is real expertise. Many people use databases for 20, 30 years, but they don't bother to read the advanced chapters. I'm going to talk about why that's important. I'm going to make a case for contributing back. A lot of the most popular databases are open source, but you don't see people taking time to involve themselves in that community, to give feedback to the community, to contribute pull requests, to document or answer questions. I think it's incumbent upon us as professionals to help build the profession, and open source is one of those ways. We're also going to talk about creating safe spaces for new programmers and developers to fail. You have to find a way to have your junior developers and your junior operators use databases in ways that will humble them. And lastly, I'm going to make a case that it is actually time for us to establish that we need more DBAs. We lost something valuable, and we need to hire DBAs. It's a different kind of DBA. We can't just hire a DBA for a relational database. We need a new kind of database professional that understands the full spectrum of database technologies. And in my experience, those people are rare to find, but we've needed them more than ever. So if you're interested in that, if you're interested in those North Star principles in part 4, we're going to establish them independent of vector databases. And then in part 5, we're going to apply those principles to vector databases. Now, this is a rapidly changing area. I hope you heard something in this episode that might help you when you're doing more research. I want to encourage you, go do your own research. All too often with databases, what I see is people end up using the database that someone else chose just because. Oh, why do you use MySQL? Well, that's what we've been using all along. Why do you use Postgres? Well, that's just the database we have. With vector databases, this is your chance to do the research, to understand what the differences are between Weaviate, between Milvus, between the Google Spanner vector search implementation or pgvector. Before you step into this space, understand what it is doing and what the differences are between the products that you choose. Because with databases, it doesn't move very quickly. And often, the first database you choose is the database you end up being stuck with for the next decade. So, no pressure, but it's time to make a decision based on your own research, because there's no DBA to rely upon anymore.